This itself can be treated as the definition of simple harmonic motion. If this type of force acts, then the motion is of something like this: right, left, left, right, right, left, left, right, right, left, left, right. And it goes on and on and on. When we say minus sign here, there is some position which is called the mean position, which I have denoted by x equal to 0. On the right side of it, I am calling it as plus x. So when you have written minus vector x, then x vector is on the right side and minus means f will be on the left side. Now, if x is on the right, then f is on the left. If x is on the left, then f will be on the right. F will always be in opposite direction to x. Now, since we have already talked about the mean position, we can also say that vector f is always towards the mean position. If x is on the right, f is on the left, mean towards the mean position. If x is on the left, because of minus sign, f is on the right, that's also towards the mean position. So no matter where particle is in its journey, vector f will always be towards the mean position. You may be wondering, how can we have a force like that? In case you are wondering, just wait. You already know that type of force. But before I talk about that, little bit more math. Now, I'm talking about the net force here. And net force is MA. Now, note that in some books, this vector sign is somewhat dropped, and that gives rise to confusion. Because if somebody says f is minus kx and doesn't say it's vector, it can create all sorts of confusion. So it's not that it's not a vector, it is a vector. If you find a minus sign in any textbook, then take it for granted that there's a vector here also, there's a vector here also. Minus sign only tells that the directions of the two vectors are opposite. That's it. And many times, for the sake of convenience, we don't talk about vector notation and we just say f equal to kx, right? If we say f equal to kx, it means magnitudes. Direction wise, always they will be opposite for SHM. Now f is MA, and I'm dropping that vector symbol, so I'm just taking the magnitude MA equal to kx. Okay, so A is k by m into x. It is a common practice to use omega square for k by m. It's a very common practice. So A is omega square x if we talk about just the magnitude, but if we talk about vector, there would be a minus sign. Now this omega is not your angular velocity of circular motion. Where is the circular motion here? There is no circular motion here. It's a straight line motion we are discussing. We are discussing linear SHM right now. Later on we will also come across angular SHM, but right now it is linear SHM. Its motion is taking place in just one line. So there is no question of circular motion and angular velocity. So don't call it angular velocity. Omega is root of k by m. Okay? So that's about omega. Now, talking about a real situation. As I said, you already know that thing in which this type of force is there. If it came to your mind, then let me know what it is, something that you know of. Yes, that's right. Spring force. Consider an ideal spring, smooth surface and some particle M. You pull it or compress it and release it and just watch what happens. That's exactly what SHM is about. You will find that from the initial unstretched position, if displacement is x, initial is the position which is unstretched position. From that, if the displacement is x, then the force will be minus k vector x, right? That's how spring behaves. If this is the unstretched position and you pull it to the right side, spring won't like it. Spring will apply force on the left side. So x vector is on the right side and force vector of the spring is on the left side. So what happens if you pull it to the right side and you release it? It goes to the left side. It comes to its original position, but it doesn't stop there because it has got kinetic energy. When you pulled it, the potential energy got stored, and then it started moving to the left side, and when the spring acquired its natural length, then the spring potential energy became zero, but all of it that was stored got converted into kinetic energy. So in fact, when it passes through that point at which spring is at its natural length, all energy is kinetic energy. That means the speed is maximum. No question of stopping there. So it will overshoot that position and will go to the left side. This is where spring has got its natural length. It's going to the left side. Now it compresses the spring more. Spring doesn't like being compressed. So spring applies force on the right side. That slows down its speed. Force on the right side, speed is on the left side. Slows down. and finally it stops. Say it stops somewhere here. Now, at that particular point, spring is compressed to maximum extent, and spring doesn't like being compressed. Spring likes to have its natural length. Now spring pushes it to the right side. So it moves to the right side now. Spring is trying to acquire its natural length. The block is gaining its kinetic energy. And then spring acquires its natural length, but then block has got a lot of kinetic energy, maximum. And it doesn't let spring rest at its natural length. The speed of m makes it go to the right side further. Again spring becomes longer, which it doesn't like. So this game goes on and on and on and on and on. And theoretically it will go forever. But real life is not about smooth stable. Real life is not about zero air resistance. So in real life you will always find that it will stop eventually. But we are talking about an ideal situation. There is no friction anywhere. Net force is minus kx vector. Now here, one thing can be shown mathematically. Say this is the extreme left and this is the extreme right. This is the mean position. Say this is A, this is A dash. At A, speed becomes 0. That means all energy is spring potential energy. Here at A dash also speed becomes 0. That means all energy is SPE, spring potential energy. We are assuming no loss of energy, mechanical. So they must be equal. And there is no kinetic energy at A or at A dash. Right? And that means OA is OA dash. And this maximum distance on either side is called amplitude. Amplitude of simple harmonic motion, or in short, SHM. We will now do the mathematics which will lead us to the equation of SHM. Some particle is performing SHM, right, left, left, right, right, left, left, right, and so on and on and on. When we press the stop watch, then we find that particle is at x0, it has a speed of v0. When we press the stopwatch, and when stopwatch is reading time t seconds, then we find that the particle is here. It is having x equal to x, v equal to v. Like that. Now, net force is going to be minus k vector x at this particular point, we would need to go to acceleration, motion basically, acceleration, velocity. Or maybe I can start in this way also. Acceleration is equal to this, minus omega square x. But acceleration is dv by dt. Now every time putting vectors, now you take it that I'm using vectors. So I may not write every time, I may not draw every time that vector, but I'm dealing with vectors. In fact, calculus will take care of it. No need to worry about that arrow. Now, variable, V is variable, speed will change. Time is of course variable, position is of course variable. We don't like to deal with 3 variables. Generally 2 variables is what we like. So we apply the chain rule and we get rid of 1 variable. So this is the chain rule I am applying, dv by dx into dx by dt. What is dx by dt? Right. So that allows me to get everything in just 2 variables. V dx by dt into dv by dx equal to minus omega square x. Right? So t is gone completely. Our problem is solved. Now we can do the math, integration, etc. and we can find the relationship between v and x. Eventually we certainly want t, eventually. Actually what we want is x-t relationship. That's what we want, x-t relationship. This should eventually lead us there. So let's find out Vx relationship and then proceed towards xt relationship after that. Separating variables is very easy now. Done. Integration should be very easy also. Now I want to put the limits of integration. So when we pressed the stopwatch, x was x0, v was v0 at that instant. When stopwatch was reading t seconds, x was x, v was v. Integral will be v square by 2 from v0 to v. Minus omega square is a constant. It comes out of integral. And then we have x square by 2 from x0 to x. I can cancel 2 on both sides and then I get this thing. I want v in terms of x. Okay. So v0 square. These constant things I can group. v0, omega, x0. So x square is the variable part. At this point, we are calling this constant as a square. At this point, it may not make too much of a sense what is a, but it will make a lot of sense after some time. So right now, just think of it as something, some short way of writing, instead of writing that whole thing. Now we have this short thing. So that is V in terms of X. We already got it. We want XT relationship. That should be no problem. V is dx by dt. Any questions up to this point? If you have, then let me know. Looks like no questions. Well, separating variables is no problem at all. Now, we need to integrate. When stop watch was pressed, t was 0, x was x0, and when the stopwatch reads t seconds, x is x. This integral has a standard result, tan inverse x by a. Omega is constant. In fact, when we define SHM, there itself you can make note that k is a constant and omega is a constant. K is a constant, not universal. It is a constant for a particular SHM. Omega is not a universal constant. It is a constant for a particular SHM. When mass goes to the right, left, left, right, etc., many things change. Speed changes, acceleration changes, force changes, x vector changes, speed changes. But k doesn't change. Omega doesn't change. So k and omega are constants for a particular SHM. They are not universal constants. So omega comes out of integral t from 0 to t. Now putting x in place of x, putting x0 in place of x, t in place of t, 0 in place of t. x0 is constant a. A is constant, isn't it? Again, for a specific SHM it is constant. A depends on what? x0, b0, omega. So A is constant for a specific SHM. x naught is constant for a specific SHM. And since it is sine inverse, it is an angle. For angle, I am using delta sine. So delta is sine inverse x naught by A. Now that means sine inverse x by A is omega t plus delta, which implies that x by A is sine of omega t plus delta, and we got our relationship x and t, A sine omega t plus delta. As time changes, x changes. Capital A is, okay, that we will see now. What is capital A? As t changes, x changes. But you know the maximum value of sine is 1. So maximum value of x is A. But what is maximum value of x called? Amplitude. And that means A is not anything but the amplitude itself. So while in this step that was not clear what actually A was, now it is clear that A is the amplitude of the specific SHM under consideration. So A is the amplitude, omega is a constant, delta is sine inverse x naught by A. X naught means when you press the stopwatch, then where was the particle? Initial state. Delta tells you about the initial state when the stopwatch was pressed. It is an angle. We are discussing linear motion, but it is an angle. Obviously, this angle cannot be for the motion. This angle, I mean, it's a straight line motion, right? But you must be thinking that we have used omega symbol. Omega symbol was used in circular motion or in rotational kinematics. And now we are using delta angle, again angle, circle, that idea of circle. Is there something we are trying to find relationship sort of with circular motion? And the answer to that is yes. But the motion is a linear motion. Actually, linear motion can be related to circular motion. Piston in a vehicle moves performing linear motion, and the wheel rotates. Linear motion and circular motion do have something that connects them. Linear motion and circular motion do have something that connects them. And here our particle is not performing circular motion. Our particle is performing linear motion only. But maybe somebody else is performing circular motion. And that thing which is performing circular motion is not a particle, but is something that we visualize. And then there is a relationship between circular motion and linear motion. You will see it after we have done some more theory. It's very, very simple. How a circular motion can be related to a linear motion. So that's why we are using these symbols, omega, delta. So delta has to do with the initial state. Now that particle is performing SHM, right, left, right, left, right, left, right, left. It is you who presses the stopwatch. Maybe somebody pressed the stopwatch and that instant particle was going to the left. So many things are possible. So delta has that information in it. So this is the xt relationship. Vx relationship we already have. Very important one. It's a standard result. Then what will be the maximum V possible? When there is no potential energy, all energy is kinetic energy. That's how V can be maximum. And from spring analogy, you can say that it must happen at x equal to 0. But this is only analogy. Note that we are not defining SHM motion only working for spring system. Spring is an example of SHM motion. There can be several other motions. So while K sounds very well with spring, K immediately gives you the picture of spring constant. But don't think that this K is always spring constant. On many occasions, it has nothing to do with spring constant. There is no spring anywhere in SHM. So K is not necessarily spring constant. It may be spring constant for certain specific type of SHM like this one. But at this point, I will have to use spring analogy to talk about maximum speed. So think of the mean position where x is 0, so spring has no potential energy stored in it. All energy is kinetic energy. Using that analogy, it is very easy to tell what would be Vmax. Look at the bottom of this board, board number 3, and put x equal to 0. And you get V equal to omega A. But that explanation makes use of spring, and one can say that SHM doesn't have to involve spring in all cases. So how can we generalize that V maximum will be omega A? That's a good question. How do we generalize that V maximum equal to omega A? Well, that's not difficult also. If you want to generalize without making use of a specific situation like that of spring, then differentiate x equal to A sine omega t plus delta. So when you differentiate it, what do you get? You get dx by dt equal to A sine A omega cos omega t plus delta. Dx by dt equal to A omega cos omega t plus delta. Now that's a general result, not only valid for a spring particle system, any SHM. And you know the maximum value of cos function. Maximum value of cos function is 1. So the maximum value of V is A omega. Right? So A omega is the maximum value of V. Now, XP relationship we have written as A sine omega t plus delta. In some textbooks you may find it to be written as cosine function, maybe A cos omega t plus something type. That's no problem at all, because sine and cos functions are similar, okay, I should say this way, they have similar behavior. Let's use the graphing calculator. So if I type y equal to sine x, if I type y equal to cos x, both I am plotting on the same graph. They are similar functions. It is just about right-left shift. Just shift one little bit and you get the other one. So just by changing that delta, you can have another thing, sine cos, sine and cos, cos and sine, 90-degree thing. 90-degree shift is all you need. So x and t, sinusoidal or cosinusoidal, it's the same story. It has to do with the t equal to 0 situation. When you press the stopwatch, where was the particle? Not only where was it, in which direction was it going also is important. Where was it and in which direction was it going? Delta has the answers to these questions. Next, we define the meaning of the word oscillation, complete oscillation. That's easy to understand. Suppose when you press the stopwatch, particle was here and it was going to the left. One oscillation complete would mean that when does it happen next? You will say many times. When will it happen next means both should be same. Vector x also and vector v also. So it goes here, comes back. No, not then, because then it's going to the right. So it goes left, goes to the right and then left. Then it happens. So here. That is called one full oscillation. Right? And when we say time period of oscillation, it means time taken to complete the full oscillation. And it doesn't matter when you press the stop watch. T is always going to be the same. So if somebody presses here, then this journey, then this journey, then this journey. Right? And if somebody presses the stopwatch here, then this journey, then this journey, then this journey. T is always going to be the same for one full oscillation. And by time period, we mean time taken to complete the oscillation. And we denote time period by capital T. Formula for capital T is very important. It is used a lot. So how do we get it? The rule is that both x and v must be same. Both x and v must be same. And when that happens in the shortest duration, then that is T. The shortest duration after which both x and v are same, that is the time period. So x is given by a sine omega t plus delta, and v is given by a omega cos omega t plus delta. Now they both must be equal after the minimum time called capital T. That means a sine omega t plus, let me write like this, omega t plus delta should be equal to a sine omega t plus delta, and a omega cos omega t plus delta equal to a omega cos omega t plus delta. Would you like to try to solve these two simultaneous trigonometric equations and try to find out the minimum value of capital T, shortest? See if you can. I can give you the clue if you need. The clue which can solve this situation. Sine and cos functions, they both repeat together after 360 degrees. Both sine and cos have to repeat, right? And they both repeat after 360 degrees. Minimum is 2 pi. Otherwise it can be 4 pi, it can be 6 pi, it can be 100 pi. But the least angle after which they both repeat is 2 pi. And now see if you are able to get the result for T. This is the bracket. I was just saying that sine and cos functions both become equal after a minimum angle of 2 pi. But since there is a bracket, I don't think you should get 2 pi for T. And T is time, so it can't be equal to angle. Okay, this is what I was saying in different language. If sine theta is equal to sine phi, and if cos theta is equal to cos phi, if both equations are simultaneously true, then it would mean that the minimum gap between theta and phi is 2 pi. Both conditions are satisfied after 2 pi angle. This is what I was trying to say. So then what should be the answer for capital T? You are getting P equal to 2 pi by omega. That's what you should be getting. That's right. So we would have then this minus this equal to 2 pi, and that means omega t is 2 pi, or t equal to 2 pi by omega. And how much was omega? Root k by m. This is most likely the most used formula in this topic. Any question? Let me know. I'm not looking for yes or no type of answers. Explanation is what I'm looking for. Okay, I can see that answer in private message. You're right. And the answer is this. This happens when actually x is maximum. This is happening when x is A. And that means force will be maximum. So does speed mean force is zero? No. If some object is kept at the ground, stationary in the beginning, and then it moves, some force has to act, isn't it? So where is the Newton's first law here? If V is 0 and then V is not 0, then it means there has to be some force. V is 0, right. But then after some time V is not 0. Particle goes to the left. Its speed only increases after that. So there has to be some force which is changing V. But sometimes students do make this mistake, that at extreme positions there is sometimes a feeling that it is equilibrium. Sometimes mind relates equilibrium word to V equal to 0. That's the problem. So V equal to 0, then in your mind, if this thought comes, it is equilibrium, then this thought can also come after that, that F is 0. So the answer is that F is not 0, F is maximum because of this and is acting in opposite direction at extreme positions. It doesn't need to be long explanation. A particle executes SHM if you are told that its velocity at this instant is 0. Can you say what is its displacement? That's number one. If you are told that its velocity at this instant is maximum, can you say what is its displacement? Explain. Okay, that's your assignment question.